Okay, hello everyone. Today we will learn about estimation part 3. Chapter 8.6 is about large sample confidence intervals. When we have large number of samples in our problem, usually we can approximate our point estimators by normal distribution and use that distribution assumption to calculate the confidence interval. Here we describe some frequently used cases. So for large samples, all point estimators for mu, p, mu1 minus mu2, p1 minus p2 have approximately normal sampling distribution by central limit theorem. So the table here is also you have seen this from section 8.4. For our interesting parameters, mu, p, mu1 minus mu2, p1 minus p2, our pointer estimators are here and standard errors are here. And with this information, we approximate approximate our point estimators using central limit theorem, derive the normal distribution that follows, and then use that distribution to calculate confidence interval. That's the strategy used in section 8.6. Let's solve this example 8.6 to understand how we can use the normal distribution to do the inference about the confidence interval. This is a simple example, so let's try to do this. Example 8.6. Let theta hat be a statistic that is normally distributed with mean theta and standard error sigma theta hat. Find the confidence interval for theta that possesses a confidence coefficient equal to 1 minus alpha. Before we solve this problem, we know that the theta hat minus theta divided by its standard error, sigma theta hat. This follows the standard normal distribution, z with mean 0, standard deviation 1. So we know the distribution of this thing. Let's say this new variable is z, and we know this z follows the standard normal distribution. And so we can use the probabilistic inference. The value z follows this standard normal distribution, and let's say this part is the probability for this part is alpha over 2, and probability of this part is again alpha over 2. So if we decide to make a two-sided confidence interval, let's put side probability equally. So the probability for the parameter is inside. Here it is 1 minus alpha, and so this can be written like this. The probability of our standard normal variable z is from lower bound to upper bound is 1 minus alpha. This is the probability. And so what we need to do is we rewrite this part. So this part is probability of, we multiply the standard error in both sides, left-hand side and right-hand side, then we will get z alpha over 2 times sigma theta hat minus theta. This is z alpha over 2 times sigma theta hat. And we take minus to each side, and we plus theta hat, then this part becomes probability of theta hat minus z alpha over 2 times sigma theta hat is theta hat plus z alpha over 2 sigma theta hat. Okay, so what we know now is that the probability of lower bound and upper bound enclosing theta is 1 minus alpha, and that's what we want to calculate. So find the confidence interval for theta that possesses a confidence coefficient equal to 1 minus alpha. This is that. So the confidence interval for this case should be, this is our lower bound, and this is our upper bound. So here formula for 100 times 1 minus alpha percent confidence interval would be this. Okay. Okay, let's move on to more realistic example, which is example 8.7. The shopping times of n equals 64 randomly selected customers at a local supermarket were recorded. The average and variance of the 64 shopping times were 33 minutes and 256 minutes square, respectively. So they are mean and variance. And estimate mu, the true average shopping time per customer, with a confidence coefficient of 1 minus alpha equals 0.90. So the problem is to calculate the confidence interval for mu. What would be the lower bound and the upper bound? And the probability of this thing is 0.9. Okay. And to do that, we need some probabilistic distribution related to this thing, which is what we know is y bar minus mu divided by standard deviation of y bar will follow normal distribution with central limit theorem. This is what we know, and unfortunately, we don't know the variance. Actually, this term is unknown. So what we should do is we should put the estimator for sigma y bar. So if we put the estimator, which is actually the estimator would be s squared divided by n square root of, so this is the variance, and we can estimate our standard error with this thing. And if we do this, actually, as we learned, this follows the t distribution. So y bar minus mu, if we because this thing follows chi-square distribution, and s square and y bar are independent. That's what we learned. So if we replace here s square divided by n here, this thing follows t distribution with n minus 1 degrees of freedom. And for the t distribution, if n goes to large, then this one can be approximated as normal distribution, normal 0, 1. So when as n goes large, and actually this is because as n goes large, this thing converges to standard error of y bar, and converges in probability. So this one can be approximated by the normal distribution when the sample size is sufficiently large, which is our case. So what we will do is that in the previous example, example 8.6, we derived that the lower confidence bound is theta hat, which is y bar here. This time, theta hat minus z 1 minus alpha over 2 times sigma y bar. And actually, from here, we want to use the estimate for this thing. And this is our lower bound, and let's try to calculate it. So y bar is 33, and the z 1 minus alpha over 2, which is alpha is 0.1, z Oh, this is Z alpha over 2. Anyway, Z alpha over 2. This is 1.645 from the table, or you can also use R using qnorm command. Qnorm 1 minus alpha over 2. Then it will return the value, which would be 1.645 in R. You can check it. So since you are solving these problems online, and we will probably going to have online exam, so maybe you can use R. So to find the value for Z alpha over 2 in R, you can put Q norm 1 minus alpha over 2, then you will get about 1.645 dot dot dot. Okay, and so let's try to solve it. 33 minus Z alpha over 2 is 1.645, and times sigma y bar estimate, which is square root of s square, 256 over 64, and so by using calculator you can calculate it. The value is 29.71, and also you can calculate the upper bound, which is y bar plus z alpha over 2 sigma y bar hat, and this is 33 plus 1.645 square root of 256 divided by 64, and this is 36.29. So your confidence interval would be 29.71, 36.29. Okay. Let's move on to example 8.8. Two brands of refrigerators denoted A and B are each guaranteed for 1 year. In a random sample of 50 refrigerators of brand A, 12 were observed to fail before the guarantee period ended. An independent random sample of 60 brand B refrigerators also revealed 12 failures during the guarantee period. Estimate the true difference P1 minus P2 between proportions of failures during the guarantee period with confidence coefficient approximately 0.98. And actually, from the table that we learned from 8.4, the estimate for difference of proportions, so for P1 minus P2, the estimate for P1 minus P2 should be P1 hat minus P2 hat. And the standard error for P1 hat minus P2 hat, this would be square root of N1 here, P1 times P2 over N1 plus P1 minus P1, 1 Q1. Wait a minute. 1 minus P1. Okay. P2, 1 minus P2, and N2. Okay. And so the in previously in example 8.6, we derived that the confidence interval is zeta hat plus minus z alpha over 2 times standard error of zeta hat. And from here, actually, since we don't know the exact value for P1 and P2, the sigma, this value is unknown. This value is unknown. But with large sample case, the sigma hat of P1 minus P2, this one converges to sigma P1 minus P2 hat, converges in probability. So we can approximate this thing use hat, and this hat for this thing we estimate it by putting these to hat, putting estimates for P1 and P2. And what are P1 hat and P2 hat? And from here, P1 hat is among 50, we have 12, so 12 over 50, which is 0.24 is P1 hat, and P2 hat is 12 over 60, which is 0.2. Okay, and so now we can calculate lower bound and upper bound. So what would be the lower bound? The lower bound is 0.24 minus 0.2 minus z from here 0.02 over 2. Z alpha is 0.02, so z 0.01. If you calculate this, this would be 2.33. This would be 2.33, and so this is 2.33 times square root of 0.24 times 0.76 divided by N1 50 plus 0.2. 0.2 times 0.8 divided by 60. Okay, and to calculate this, you will get minus 0.1451, and you can calculate the upper bound 0.24 minus 0.2 plus, and this thing is same, and if you calculate the upper bound, this is 0.2251. So the confidence interval for this case is minus 0.1451, and upper bound is 0.2251. Okay. Figure 8.8 explains the situation of the confidence interval. In confidence interval, we calculate the probability of lower bound, which is actually, let's write this way, theta hat minus z alpha over 2 sigma theta hat. Theta hat plus z alpha over 2 sigma theta hat is this is 0.1 minus alpha. Okay, 1 minus alpha. From here, if we take alpha as 0.05, then this is 0.95, and the explanation is something like this. If we calculate since theta hat, this is a random variable, so this part is random. These two parts are random, so the confidence interval is randomly decided, and so what this implies is that the probability of our confidence interval is enclosing the true parameter theta. So let's say this 0.5 is the true parameter theta. The probability for our confidence interval to enclose the true parameter theta is about 95%. So here's 24 realizations of our confidence intervals. When our trial goes large, and about 95% of times our confidence interval would include the true parameter estimate. That's the interpretation about the confidence interval. Okay, let's move on to exercise problem 8.56. Is America's romance with movies on the wane? In a Gallup poll of n equals 800 random chosen adults, 45% indicated that movies were getting better, whereas 43 indicate that movies were getting worse. Find the 98% confidence interval for P, the overall proportion of adults who say that movies are getting better. Okay, so movies are getting better. 45% indicated that movies are getting better. So 90% confidence interval for that would be as I mentioned, the confidence interval can be derived as zeta hat plus minus z alpha over 2 times sigma theta hat. And actually, we can replace this sigma theta hat with sigma hat for large samples. So we were going to use this formula, and theta hat in this case is 0.45 and plus minus z alpha over 2. Here alpha is 0.02, so z 0.01 times what is sigma hat, which is square root of P1 P2. P1 is P1 Q1 0.45 times 0.55 divided by 800. Okay, so this is our confidence interval, and here z 0.01 is 2.326. Okay, so if you calculate the bound by using calculator, you can calculate this bound is 0.409, and the upper bound is 0.491. Okay, so this is answer for question A. And what would be answer for question B? Does the interval include the value p equals 0.5? Do you think that a majority of adults say that movies are getting better? And the parameter for movies getting better, the confidence interval of this thing do not include p equals 0.5. So I don't think we don't think that the majority of adults say that movies are getting better, because the p 0.5 is not included in our confidence interval bound with 98% of confidence interval. You can say that as an answer for B. Okay. And homework for 8.6 are these. Next chapter, 8.7, is about selecting the sample size. In this problem, this is how many sample n do we need for error of estimation. So in our confidence interval calculation, it represented like this. We have point estimate and plus minus error of estimation b. So our confidence interval calculated from this formula. And how many sample n do we need for a certain number of error of estimation? So here we will set the error of estimation equals b, and in here we should note that this sigma the standard error of theta hat. The standard error of theta hat is proportional to 1 over square root of n. So since this equation holds, if we set this equation, we can derive n with respect to b. So from this equation, because the standard error of theta hat, this one is proportional to 1 over square root of n, we can derive this, we can derive n equals something from this formula. Okay. Okay, let's move on to example 8.9. The reaction of an individual to a stimulus in a psychological experiment may take one of two forms, A or B. If an experimenter wishes to estimate the probability P that a person will react in manner A, how many people would be included in the experiment? How many people must be included? How many samples do we need? And assume that the experimenter will be satisfied if the error of estimation is less than 0.04 with probability equal to 0.9. Assume also that he expects P to lie somewhere in neighbor of 0.6. Okay, so we want to calculate the sample size n, and in the problem, we want to have our error of estimation b is less than or equal to 0.04. And what is b? B is error of estimation, which is z, and what is alpha? Here alpha is 0.1. From here, we can calculate alpha from here, and so for z, alpha over 2 is 0.05, 0.05, and sigma p hat. So this is our error of estimation, and we want to have our error of estimation is less than 0.04, and so we want to use this formula. Okay, so what is z 0.05 is actually 1.645, and rather than calculating standard error of p hat, we estimate this since so the formula for this is square root of n p hat times 1 minus p hat. And from here, actually, if we don't have this, so if we don't have hat, the formula is this one. And since we don't know the p, we should put something here. But in the problem, assume also that he expects p to lie somewhere in the neighbor of 0.6. So we can put 0.6 in p here. So this is 1.645 square root of n here, and p is 0.6, and 1 minus p is 0.4, and this is less than or equal to 0.04. And so we can derive this with respect to n. So if you solve this with respect to n, you can find that this can be rewritten as actually n is greater than or equal to 405.904 or something. So we can conclude that we need 406 samples. Okay, sometimes we don't have information about p. Sometimes we don't have information about p, and in that case, if we rewrite this thing, this can be written as n is greater than or equal to p1 minus p times 1.645 squared divided by 0.04 squared. And here, this is function of p times 1 minus p. And the p times 1 minus p, so p times 1 minus p, the graph of this is something like this. And p, this side is p, and this side is p times 1 minus p. And p times 1 minus p is maximized when p is 0.5. And so to have this equation, to have this equation always hold, we put p equals 0.5 and calculate n. So in that case, if we put 0.5 inside of the p, then we will get the value of 422.82. So if we don't have this additional information, the n, the sample we need is 423. So yeah. So answer for example 8.9 is this one if we have this condition, and if we don't have this additional condition, the sample size is 423. Okay. Let's move on to example exercise 8.74. Suppose that you want to estimate the mean pH of rainfalls in an area that suffers from heavy pollution due to the discharge of smoke from a power plant. Assume that sigma is in the neighbor of 0.5 pH and that you want your estimate to lie within 0.1. So this is our B of mu with probability near 0.95. So your alpha is 0.05. And approximately how many rainfalls must be included in your sample? So what sample size do we need? This is the problem. Would it be valid to select all of your water specimens from a single rainfall? Okay, so let's try to solve the first one first. We need to calculate the sample size, and the B, we want to have our B is less than or equal to 0.1, and our B is Z alpha over 2, which is 0.025, and here sigma mean pH. Okay, so this would be our formula, and here Z 0.025 is 1.96, approximately 1.96, and sigma y bar, this is square root of sigma over n, and this here sigma is near neighbor of 0.5, so sigma is 0.5, and is what we need to calculate. So the equation becomes like this: 1.96 square root of 0.5, and here n is less than or 0.1. So this becomes and go this side 0.1 squared 1.96 squared 0.5. Okay, so if you calculate this number, actually sigma squares to 0.5 square, because sigma is 0.5, and in the formula this is sigma square over n, So this is 0.5 square, and if you calculate this number, the number is 96.04. And since n should be greater than 96.04, and our n is 97, so we need 97 samples. And the second question is, would it be valid to select all of your water specimens from a single rainfall? And actually, if we select all of our samples from a single rainfall, then our samples would not be independent. So since we need independent samples, so the answer to this question is no. No, it's not valid. Okay. And here is a homework for chapter 8.7.